Okay, so we have just finished calculating arc lengths for functions in the form y equals f of x, and the formula is not so elegant or easy to work with. What we'll find is that the formula is much more elegant if we look at curves that are defined parametrically. So you probably don't remember parametric equations completely, so let's do a quick review of parametric equations. Okay, so here's a very basic example where x equals 2t and y equals t squared. So let's remind ourselves of how to handle one of these problems. If I had to make the graph of this, just like any other problem where I don't know what the graph looks like, I could make a t table, but this is because it's no longer a t table, it's a 3-column table. Where both x and y are functions of time. So let's put in a few values. Let's put in time 0, 1. I should say it's a function of t, where t is often time. So let's just work our way up to 4 seconds if that were time in seconds. So you can see that the x values would be 2 times the t values. So it would be 0, 2, 4, 6, and 8. So these are linear. Okay, the values are increasing in a linear way. If I substitute in for y equals 0, 1, 4, 9, and 16, since y is just the t squared. So these are parabolic. Right, now if we go to graph this, let's make a graph. Okay, we only need a first quadrant, so let me put the graph like this. Okay, and we may run off of the graph, but we can put these points onto the graph. So let's see, the first point would be at 0, 0. The second point is at 2, 1. The third point is at 4, 4. So I'm using unit markings as on the grid as units of x and y, and then 6 and 9, 4, 5, 6, 7, 8, 9. I'm going to stop there. If I were to sketch in the curve, it looks like it will do something like this. Keep on going up. It looks kind of parabolic. All right, the reason it looks kind of parabolic is because it is parabolic, but we'll get into that in just a moment. All right, now there's more information that this graph gives me than just the shape of the curve. So typically when you look at a curve, it's a static thing. But this tells me that when t equals 0, I was here. This tells me not only where I am or what the curve looks like, in other words, the entire path, but it tells me when I'm at each point. All right, so I can see that the points are getting further and further apart. So if this were describing motion, we would be speeding up. Now, because we're speeding up faster in the y direction, eventually this path curves. If we were traveling at this constant rate in both directions, as we are in the x direction, we keep going up by 2s, then we would have a straight line if we also went up by a constant amount in the y direction, but we don't. These go up parabolically, so we get a curve, all right? Now, I said this would be a parabola. I can quickly prove that. You're used to algebraic parabolas. I can say that, let me scroll down just a little bit here. If x is equal to 2t, I could say that t is equal to x over 2. And since y equals t squared, y must equal x over 2 squared. So it's pretty easy to see that y must be 1/4 x squared, which is pretty classic parabola. Now, as I said before, this gives me the shape, but it doesn't tell me where I am when, okay? It's less information. It's the shape, but less information. If we were trying to describe motion, I would want the parabolic forms of the equations, and rather than just the fact that it is a parabolic path, all right? Now, you actually, in physics, let me just do a quick aside. Whoops. In physics, scroll that out, jumped on me. In physics, you use parametric equations all of the time if you do projectile motion. So let's just look at projectiles. Okay, so if you have projectiles, you have that x of t is equal to v naught x times t. And you have that y of t is equal to y naught plus v naught y times t minus 1/2 g t squared, right? So this, in fact, is a pair of parametric equations. And like the example I just gave you, this is linear in the x direction, and this is quadratic or parabolic in the y direction. And if I were to substitute in that t is equal to x divided by v naught x, I would in fact see that it is quadratic for y in terms of x, so it is in fact a parabola. So we could do that. Hopefully you remember from physics that if you had a projectile that was launched at some angle theta, we could figure out v naught x and v naught y based on how fast it was launched and the angle at which it was launched. So a lot of physics deals with parametric equations because we're very interested in how things move through space over time. In fact, we are likely to add later on, and you'll get to this in multivariable, you'll add a third dimension. So you could handle motion into all 3 dimensions. All right. Another example of kinds of things we might want to do parametrically. Let's call this example 2. Let's say that x is equal to 2 cosine of t and y is equal to 3 times the sine of t. All right, you might recognize what this will be, but let's make a t-table and figure this out. Call this a 3-column t-table. Now, if we're working with sines and cosines, I don't want to put in integer values. What I want to do is put in things like pi over 2 and pi and 3 pi over 2 and 2 pi. So let's work our way around with the cosine function first. At 0, it's 1. So the total x value is 2. Then it's 0. And if I put in pi into cosine, I get a -1. So I get a -2 overall, 0, and then back to 2. I do the same thing in the y column. The sine of 0 is 0, so I start at 0. At pi over 2, the sine of pi over 2 is 1, so I go up to a y value of 3. Back to 0, down to -3, and back to 0. You can check those values out if you wish, but I can now make a little table or a little graph of motion. And let me make the graph look like this. And at time of 0, let me put in my red points. Okay, you start at 2, 0. When the time reaches pi over 2, you're up at the top at 0, 3, and then we're over here at -2, 0, 0, -3, and then back to the beginning. So at time 0, so we know we go around in a path that looks something like this. We're circling around, so to speak, although it's not a circle. And this was t equals pi over 2. This was t equals 3 pi. I'm sorry, t equals pi. T equals 3 pi over 2, and then back to 2 pi puts us at the same place that we started from. Okay. You may remember we could put numbers in front of the t. If those numbers were bigger than 1, we could speed up how fast we were going around this rotation. If we made it smaller than 1, we could slow our rate of rotation down. So all of those are useful things. We could change the 2 and the 3 to vary up how much it stretches in the x and y direction overall. So those are all things we could change. But we can show that this shape is an ellipse. What I have given you are the parametric equations for an ellipse. We can control how fast we go around the ellipse. It's very easy to write the equation of an ellipse parametrically. I can show that it's an ellipse, though, because I know that the cosine of t must equal x over 2. And I know that the sine of t is equal to y over 3. And I know that cosine squared of t plus sine squared of t must be 1. Okay, the Pythagorean identity, that must be true. Okay, so if I put that together, then x squared over 4 plus y squared over 9 must equal 1. That was the general form that you had when you were studying ellipses back in pre-calculus. So that's how we could make an elliptical path. Now, what we're going to be interested in is determining the lengths of these curves. So if I have something moving along a parabola, I might want to know how long that path is, right? If I have something moving in an elliptical path, I may want to know how long that path is. So what we're going to be doing in the rest of these videos is trying to determine how long these paths might be.